In today's lesson, we're going to learn how to find the slope of a tangent line to a curve at a given point. Now, I want you to think back to when you were taking geometry, and your teacher probably defined tangent line as as a line that is tangent to a curve at a single point. And she might even specify that it only touches that circle at a point. Well, that definition is true, and it works great for circles, but when we have more complex curves, that definition starts to fall apart. So over here, I have a little bit more complicated curve. Now, if I use this definition of tangent line, say at this point here, we'll call this point P. Now, tangent line, there it only touches a curve at one point, and that point that I filled in. But if I extend that line out, and we know lines go on forever and ever, it ends up hitting the curve again. Even though it hits the curve at a point, this is still a tangent line. And that point in which it's tangent to the curve, we call the point a tangency. So since the definition has changed a little bit, we need to go back and just kind of get some misconceptions that we might have about what makes and what does not make a tangent line. So the first misconception is that a line is tangent to a curve if it crosses the curve at exactly one point. So line L here crosses this curve at point P, but it is not a tangent line. So just because it crosses it once does not necessarily make it a tangent line. Now here on the right-hand side, we have misconception too. A tangent line is a curve must cross the curve only once. Here, this is a tangent line, but it crosses the curve more than once. So we have to expand our definition to say a tangent line may cross the curve more than once. We're focusing on that it's tangent at that point P. P is the point of tangency. Another misconception, a line is tangent to a curve if it touches a curve at one point but does not cross the curve. Well, L2, that line L here clearly does that, but it does not make L a tangent line. Here, on the other hand, a tangent line to a curve is a line that just grazes a curve to a point but does not cross it. Well, L here is a tangent line, and it obviously is obviously tangent, and it crosses the curve. So these two examples on the right are tangent lines. The two examples on the left are not tangent lines. So let's do some investigation. How would I find the slope of a tangent line? So let's go back to when we learned how to find the slope of a line. And you probably learned it as that y2 minus y1 over x2 minus x1, or the change in y over the change in x. We are still going to use that basic definition of a slope, but we're going to have to do a little bit more because we have a problem when we try to find the slope of a tangent line. Our problem is that we only have one point on the line that we know. It is the point of tangency. So how do I use the equation above, the change in y over the change of x, when I don't have a change? I only have a single point. So in order to figure out solve this problem, we're going to start by approximating the slope of the tangent line by finding some secant lines, and we're going to get these secant lines closer and closer and closer to the tangent line. Refresh your memory, a secant line is a line that intersects the curves twice. Here's a graph illustrating what we're talking about. That blue line is a secant line, and we're going to approximate the slope of the tangent line at point C, f of C. There's our point of tangency. And we're going to use this point and then another point, which is just a little bit greater than C. So we're going to call that point C plus delta x, because delta x is a change in x. And then we're going to find the y value at that point C plus delta x. So to get a formula for us to start working with, recall that we have a slope is equal to our change in y over our change in x. So using our 2 points, C f of C and C plus delta x, f of C plus delta x. So my y on my second point is my function value at C plus delta x. And then my y1 will be my function value at f of C. that's equal to y1. And I'm going to divide this by my x2 minus my x1. So x2 is going to be the x value of my second point, which will be c plus delta x, minus the x value of my first point, which is c. So simplifying this down a little bit, our new slope of the secant line developing formula would be my f of c plus delta x minus my function value at c divided by delta x. So now what I want to do is I want to keep using these secant lines, but I want to make my delta x, the difference between my point of tangency and another point on the line, smaller and smaller and smaller. So I'm making this delta x get smaller, smaller, and smaller until it approaches 0, until the change in the x's is 0. So that's what we're looking at. And so we're going to use the knowledge we learned in the last chapter by saying to find the tangent line, the slope of the tangent line, is going to be the limit as delta x goes to 0 of our equation here for the slope of the secant line. So the slope of the tangent line is the limit as delta x goes to 0, because we want that change in the x to become nothing. So I'm getting that second point as close to the parent tangency as we can, of my y2 minus my y1 over delta x. This is the slope of the tangent line limit definition. Notice that I'll be using the notation ilm to represent slope. Let's do some practice problems. So in this first example, we're going to find the slope of the tangent line to the graph of f of x, which is x squared plus 1, at the points of tangency negative 1, 2, and at 0, 1. So let's start with the point 0, 1 as our point of tangency. So let's use this limit definition above. And since we're looking at the point of tangency when x is equal to 0, that would be our c value. So we're going to replace c with 0. So I want the function value at 0 plus delta x minus f of 0 over delta x. So plugging in delta x, or 0 plus delta x, into x squared plus 1, I get 0 plus delta x, quantity squared, plus 1. Next, I'm going to take f of x and replace every x with 0. So that's going to be 0 squared plus 1. And I'm going to subtract that from f of 0 plus delta x and divide by my delta x. And after expanding and simplifying, we end up with delta x quantity squared divided by delta x. And then I have a greatest common factor of delta x, so I can cancel that out. And that leaves me with limit as x goes to 0 of delta x. So now I'm going to do direct substitution, replace every delta x with 0. The slope of the tangent line at the point 0, 1 is 0. We can have a slope of 0. Remember that when you have a line that has a slope of 0, it's simply a horizontal line. So this happens to be a horizontal tangent line. These horizontal tangent lines will become important in later sections. So now let's try finding the point of tangency at negative 1, 2. I highly suggest that you pause the video right now and see if you can do it on your own, and then come back and watch how I work it out. Okay, so we're going to use our definition of the slope of tangent line, replacing c with negative 1. Next, I'm going to figure out what f of negative 1 plus delta x is by replacing every x in my function value with negative 1 plus delta x, which will give me negative 1 plus delta x quantity squared plus 1. And now I'm going to find my function value when every x is negative 1. So that's negative 1 quantity squared plus 1. And remember, I have to subtract that whole function value, that whole f of x term. So make sure you put the big parentheses there and distribute the negative to all terms. So in the orange here, make sure that negative gets distributed to all terms. So after some algebraic magic, I end up with the limit as delta x goes to 0 of negative 2 plus delta x. And now I'm ready to substitute direct substitution in to solve this limit equation, and I get negative 2 plus 0, or negative 2. So the slope of the tangent line at point negative 1, 2 is negative 2. So the slope of the tangent line at the point of tangency of negative 1, 2 is negative 2. Let's look at a graphical representation of what we just did in this problem. So here you see the graph f of x in black, which is the x squared plus 1. And in blue, I've graphed my two tangent lines. At the point 0, 1, notice my tangent line is horizontal. And that's when I got that slope of the tangent line is 0. And at that point, negative 1, 2, notice my tangent line is going down. And that's where I got my negative slope answer from the last problem. For this next example, we're going to do 4 things. We're going to sketch the graph, find the slope at point P, and then find the equation of a tangent line and the equation of the norm line, and then graph those two equations. So we're going to start by looking at the graph of f of x here, which is x squared minus 3, so it's my parabola moved down 3 units. And the point of tangency is this point 2, 1, which is our point P. To find the slope at point P, I'm going to use that limit definition of the slope of the tangent line. And this time, I'm going to write it slightly different so that you can get used to. Instead of writing f of c plus delta x minus f of c, I'm just going to use f of x plus delta x minus f of x. This is a more common way that you will see it written. So f of x plus delta x becomes x plus delta x, quantity squared, minus 3, minus quantity x squared minus 3, all over delta x. Now it's time to get out the algebra, simplify this down, and let's see what we end up with. We're going to do direct substitution, replace every delta x with 0. In the formula, or the equation for finding the slope of the tangent line at any given point on the function f of x is the equation 2x. So if we're going to look at the point 2, 1, the slope of that tangent line would be 2 times 2, or 4. That's the reason this is so handy formula to use instead of the c, is I don't have to redo the limit every time. I can just use the formula 2x to find the slope at any given point on that entire curve of f of x. Part C, let's find the equation of the tangent line at point P. So we're going to have to remember how to find the equation of a line. So we know the point, and the point is 2, 1, and we know the slope. So anytime you're given a point in the slope, the easiest way to find the equation is use something called the point slope form, which if you remember is y minus y1 equals slope times x minus x1. Well, you plug in the x and y value of the given point. So I'm going to plug in a 1 in place of y1. I'm going to replace with 4, and x I'll replace with 2. And then I'm going to rewrite this so I'll get y equals. My equation of my tangent line is y equals 4x minus 7. Okay, on part D, it asks us to find a normal line. So this is a new term that we haven't used yet. A normal line is the name that we give to the line that is perpendicular to a tangent line through the point of tangency. Recall, if you have two slopes that are perpendicular, so slope 1 is perpendicular to slope 2, then the product of those two slopes must equal negative 1. Or you might think of it, the two slopes are opposite reciprocals of each other. So to find the equation of the normal line at point P, I'm going to use the point 2, 1. But my slope this time is going to be the opposite reciprocal of the slope of the tangent line. So instead of a slope of 4, I will use a slope of negative 1/4. Change the sign and flip the fraction over. The procedure to find this equation will be the same. I'll use the point slope form, replacing y1 with 1 and x1 with 2, and our slope with negative 1/4. And then simplifying the equation down and solving for y. Y equals negative 1/4 x plus 3/2 is the equation for the normal line at point P. The last part of it asks us to graph our tangent line and our normal line on our equation. So I went up to section A and I regraphed that. You'll see in green is the equation of our tangent line. And in orange is the graph of the normal line. Please note how those two lines form a right angle, so they're perpendicular to each other. When you're graphing multiple equations on a single graph, make sure you label everything. Final example, we're given that L1 and L2 are equations of two lines that are tangent to the graph of f of x equals x squared, and they each pass through the point 1 and negative 3. So we need to figure out what the equation of L1 is and the equation of L2. I'm going to start this problem by figuring out the equation for the slope of all the tangent lines to the curve f of x. We will do this by using our limit definition. So the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So that'll give me the limit as delta x goes to 0 of x plus delta x quantity squared minus x squared over delta x. Expanding the binomial x plus delta x quantity squared, I get x squared plus 2x times delta x plus delta x quantity squared minus x squared all over delta x. X squared and negative x squared are like terms, so I can subtract those. I have a GCF of delta x, so I factor it out in the numerator and then cancel it with the delta x in the denominator. And that gives me the limit as delta x goes to x is 2x plus delta x. Finally, I can use direct substitution and end up with 2x. 2x is the formula to find the slope of the tangent line at any given point on the function f of x. That translates into our problem. We know the slope of L1 is equal to 2x. We also know that the slope of L1, since it's a linear equation, is equal to rise over run, or the change in y of the change in x. So using the 2 points on L1, which is the point 1 and negative 3 and x squared, there's my change in y. So my change in y is x squared minus a negative 3 divided by change in x, which will be x minus 1. So I'm using y2 minus y1 over x2 minus x1 formula. Since the slope of line 1 is equal to 2x and the slope of L1 is equal to x squared plus 3 over x minus 1, let's set those two equal to each other and solve for x. I'll first multiply each side by x minus 1. Use my distributive property to get rid of the parentheses. And then subtract x squared and minus the 3, so I get it equal to 0. Combining like terms, I get the quadratic x squared minus 2x minus 3 equals 0. Factoring that quadratic, I get x minus 3 and x plus 1. So that means x will either equal 3 or equal negative 1. So those are my two x values of the points of tangency for L1 and L2. To find the y value of my point of tangency, I just take these x's and plug it into my function. To find the first point, I will plug in negative 1 into x squared, and that gives me a y value of 1. So the point of tangency for L1 is the point 1, negative 1. I'll do the same thing to find the point of tangency for L2, line 2. So our point of tangency for L2 is the point 39. So all that's left to do is to figure out the slope of L1 and the slope of L2 so I can find the equation of each of those lines. To find the slope of L1, I will take my formula to find the slope of the tangent line, and I would substitute negative 1 in place of x. So the slope for tangent line L1 is -2. So I'm going to find the equation of a line at the point -1, 1, and slope of 2 using my point slope form. Therefore, the equation of my tangent line L1 is y is equal to -2x minus 1. Repeat the same procedure for L2. So using my formula I found in the red for the slope of the tangent line, I'm going to replace x with 3, since that's my x value at this point, and I get the slope of this tangent line is 6 with a point at 3, 9. So using my point slope formula again, y1 will be 9. So I have y minus 9 equals my slope of 6, x minus 3. And solving this equation for y, the equation of line 2's tangent line is y equals 6x minus 9.